All right, AP Chemistry students, this is Learning Objective 4, Solution Stoichiometry, and I'm going to go through some pieces of this. With the first part here, the molarity, I'm actually not going to do any work with this here. This is molarity is equal to moles of the solute divided by liters of the solution. And we have focused on this a lot already and are comfortable with this equation. So I'm not going to do anything there. The other one is the dilution one, where we have our initial molarity times our initial volume is equal to our final molarity times our final volume. So make sure you are comfortable using those two equations. What I want to do instead is to start down here with the precipitation problems, gravimetric analysis problems, and then some titration problems. Now, I actually haven't worked these out yet, so this is the answer key as I'm making it. So I might make a couple mistakes. Forgive me if that happens in advance. I'll just try to catch that as fast as I can. So first of all, gravimetric analysis is a way to be able to analyze information about a particular ion in solution. And so this one here, we're looking at information about silver. Oh, this is actually, no, we're just looking about silver chloride here. So not even about a specific ion. All we're looking for is the mass of the silver chloride precipitate. So this is probably, I guess, the easiest kind of gravimetric analysis problem that we could do, because it's just stoichiometry. We're dealing with concentrations at the beginning and we're looking for mass at the end. What's difficult here is that we have to first come up, maybe it's difficult, first we have to come up with the overall balanced chemical reaction. So CaCl2 plus AgNO3 makes CaNO3 plus AgCl. Now this is the solid, so this is the one that we're going to be able to measure. That's going to be the one of interest. We could also go backwards in future problems and figure out information about the silver in silver nitrate or something like that. So let's organize information. We have 30 milliliters of 0.15 molar calcium chloride, and then we have 15 milliliters of 0.1 molar silver nitrate. So we have information about both reactants. And if we have information about both reactants, this should be your cue to say that this is a limiting reactant problem. And with limiting reactant problems, I want to continue using that ice table method. I think the ice table method organizes data pretty well and introduces them, because we will be using them quite a bit later on. So we have 30 milliliters and 0.15 molar. That comes out to be 0.045. 0.0045. 15 milliliters and 0.1 comes out to be 0.0015. And then they decrease by x. This one starts at a 0 and increases by x. Now, before I go any further, if you're screaming at the screen, I understand. I haven't balanced this thing yet, so there needs to be a 2 there and a 2 there. So this actually increases by 2x, increases by 2x, and this one decreases by an x. So remember that in order for it to be the limiting reactant, it has to run down to 0. So we set it up like this. We say that 0, which is what it would be at equilibrium, is equal to 0.0045 minus x. So in this case, x is equal to 0.0045. Or in this case, we have 0 is equal to 0.0015 minus 2x. Oops, sorry about that. This should be a minus. Like I said, forgive me for some mistakes in advance. All right. So this means that x here is equal to 0.00075. Now, because of some math that I showed you earlier, the one with a smaller value for x, that is going to be our answer. That is a limiting reactant. And so we could subtract this out. We end up with 0. Oops, this is 0. This is 0.00375, which that doesn't really matter to us. What matters is over here, because this is what it's asking about. So we can add the 2x. So we're adding 0.015. So this becomes 0.0015 moles of silver chloride. Convert this into a mass. 107.87 grams. Oh, hold on. That's wrong. 143.32 grams. Gets us 0.215. And that is gravimetric analysis. Well, the easiest kind of gravimetric analysis problem. I mean, we're dealing with the precipitate, and that's about all that makes this the gravimetric analysis problem. Let's look at number 80. This is going to be a little bit more difficult. All right. So copper ions. This is an interesting problem here, because copper ions are dangerous to aquatic life and any kind of life. So we want to make sure that the concentration of copper ions is 0. So the fact that this plant is discharging copper ions into the water is not a good thing. And so we're looking to see exactly how much copper ions there are. So we're going to look for this molar concentration for copper ions. So that's how the problem sets up, and I can kind of gather that because of the copper ion part, and then we can read through and make sure it all made sense. So the concentration of copper ions in water, which also contains sulfate ions. So this means, all this is telling us is that we started off with copper sulfate. But what matters is that copper ion. This is useful because it may be helpful with the chemical reaction. It's discharged from a certain industrial plant and is determined by adding excess sodium sulfide with 0.8 liters of water. And here's the equation. So they give us the equation. That's awfully nice. And write a net ionic based on this, as well as finding the molar concentration of the copper sulfide. So let's go through. The net ionic is going to look like this. Sulfur plus copper makes copper sulfide. And we're looking for this guy right here. And we have 0.800 liters of it. So we're going to need moles, because we're looking for concentration. And concentration is equal to moles per liter. Got 0.0177 grams of copper sulfide, so this becomes really pretty straightforward. We're going to convert our copper sulfide into moles and then go through and do our work. There's the moles of the copper ions. Divide this by our volume. We end up with 2.3 times 10 to the minus fourth molar copper ions. Now, on a quiz or a test with this, it might tell you something like what the allowable concentration of this is, something like, I don't know, a 2%. That would be way high. It'd be like 1.6 times 10 to the minus fourth percent is the maximum that it can be. And so you'd convert this into a percentage as well and see if it is above or below that maximum. That's a common question about this, is that you're searching for some kind of a regulation or compliance and to see if it actually fits it. So then you have to do more math here. Actually, you do more math here to be able to get it into a percentage. Remember that percentage is going to be grams per milliliter. All right. Oops. Now we're into titration. We did this problem in class, so let me just do it quickly here on the tablet here so that we have it for future reference. We have our equation. Remember that KHP is a weak acid and a primary standard. And so it's a white powder, so we're able to weigh it as a mass, which is helpful. So we take our 0.4218 grams of it. I swear that's a K. You know, maybe we didn't do this one in class. Maybe we did one very, very similar to it. So, all right. That's a 6. So, there's your answer. Boy, even my 6 doesn't look like 6. There we go. Now we can go on to another one. Here we have another standard molarity type problem. Sorry, titration type problem where we are looking for some kind of an acid-base titration. We have sodium hydroxide and we've used hydrochloric acid. So here's my chemical reaction: sodium hydroxide plus hydrochloric acid makes salt water, yummy, and that part. So we can plug things in here. We have 25 milliliters of our sodium hydroxide, looking for the molarity. Hydrochloric acid is 17.4 milliliters, and at 0.312. So we can go from molarity to moles and moles to concentration. It's a 1-to-1 ratio. You know, actually, let me show you something kind of neat with this. This only works when it's a 1-to-1 ratio. But since it's a 1-to-1 ratio, we can use this relationship. Molarity of the initial times the volume of the initial equals molarity final times volume final. Remember, ladies and gentlemen, this only works when it's a 1-to-1 ratio, so be careful. But our molarity here is 0.312, 17.4 equals, molarity is what we're looking for, 25. Remember, if we have the exact same units on both sides, we do not have to cancel, or we don't have to change the units. All right, so let's go through here. I get 0.217 molar sodium hydroxide. That's our answer. Okay. Next one. Next one is a redox problem. We got a couple of redox problems coming up. All right. So iron 3 can be oxidized in an acidic potassium dichromate solution according to that chemical reaction right there. If it takes 26 milliliters of the 0.25 molar potassium potassium dichromate to titrate 25 milliliters of the iron-containing compound, what is the molar concentration of that? Now, these look scary, but they aren't. All we need to do is isolate what we're looking for. We're going from this one to this one. And so we have a mole bridge here of 1 to 6. The confusion here usually arises from this potassium dichromate and not seeing potassium dichromate up in the chemical reaction. But remember here that since this is a strong electrolyte, it dissociates 100%. So it dissociates in a molar ratio, and since for every 1 mole of the potassium dichromate we get 1 mole of the dichromate ion, whatever concentration is that we start with is also the concentration of the ion. So let me just say that again a little bit more slowly. Here is my potassium dichromate. It splits up into this. That's an R. And so for every 1 mole of this, we get 1 mole of that. And so we can also say whatever the molarity of this is also the molarity of that. All right. So we can take that and turn it into moles. Let's see here. Can I do it that way? I think so. I'm going to do it with just factor label 0.026 liters of the dichromate ions. And then molarity is moles over liter. So I can do my liters here, or excuse me, my 1 liter is my 0.025 because that's molarity. Here's molarity. Here's molarity. There's my moles. Then I can do my mole ratio step. For 1 mole of the dichromate ion, 6 moles of the iron. And then we could do the liters down here, which is 0.025 liters, and that will give us our answer in moles per liter, which is equal to molarity. So we can cancel out liter there, moles cancel. What doesn't cancel? Oops. This guy and this guy. So moles per liter. That's just another way to set this up. It's a little bit cleaner, and I've seen other students do it in the past. I tend to like the other way where we do each individual step, but putting it up on the screen like this and showing it all together, it's kind of nice. 0.26. All right, assuming I did everything right here, which is never a slam dunk, 0.156 of the iron. And that should be our answer. All right. A couple more of the redox ones. We have sulfur dioxide present in air is responsible for acid rain. Oh yeah, so that's awesome. So this sulfur dioxide is produced by car exhaust and other burning of fossil fuels, especially coal. Its concentration can be determined by titrating it against a standard potassium permanganate solution. Oops, I didn't say potassium, I promise. Well, it is. It's probably going to be a potassium permanganate solution, but it doesn't matter because it's permanganate ion. Oh, look here, wait, it is potassium permanganate. Calculate the number of grams in a sample of air if 7.3 milliliters of that stuff was used in the titration. So this is going to be a mass to or start with the mass so we can figure out the molarity. So we're gonna use molarity to figure out the mass because we have this information. So again, this is going to be the same number or same concentration for the potassium permanganate. So we can go from 7.37. Oops. I'm going to do this one the other way so you can see it that way too. So we have molarity is equal to moles over liter, which is going to be 0.008 is equal to x moles 0.00737. 9. There's my moles of my permanganate ion. Now we can go from here to the moles of sulfur dioxide and then the mass. Ooh. .4 times 10 to the minus third. Man, I'm really struggling with my handwriting today. It's even worse than normal. 3 grams of sulfur dioxide. So there you go. There's the answer for number 92. All right, let's try the last one. Oh, well, that's not very nice. I have to go back to that one there. Give me just a second. We're going to do this. I just saw that hint, and that's bothersome because I need to be able to have it in front of the screen too. So there we go. This is a really common lab done in college where you are working with iron and dichromate ions. I guess that's why it happened twice here. And so it's good to look at this a couple times. I would say that if you go to one of the major colleges, Iowa State or UNI, you'll probably do a redox titration with this reaction. So there you go. We have iron ore. Iron ore contains iron ions, but just positive 2 ions. Has 0.2792 grams dissolved in a dilute acidic acid. All of that was converted to iron 3 ions. So here's that redox. It's getting oxidized. It's losing that electron. The solution required 23.3 milliliters of the potassium dichromate for titration. Calculate the percent mass of the iron in the iron ore. So this is good. This is common. This is similar to a gravimetric analysis problem that you would see as well. We're looking for information about a specific ion. The difference here is that we're doing it through titration as opposed through a precipitate. But the process is still the same. So we're going to start with the dichromate ion. We have a molarity. We'll do it the other way. We have 0.02230 liters of the dichromate ion. And its molarity is going to be 0.0194 moles over liter. Sorry guys, my handwriting is so bad right now. It's even worse than normal. Now we're going to go from our dichromate ion to the iron 2, because that's what we're looking for. That's what is in the ore, not the iron 3. So here, incidentally, it's the same ratio, so I guess it wouldn't matter. But that would just be coincidental. Good luck. So we have 6 moles of the iron to 1 mole of the dichromate. 1 mole of the iron. Oops. I'm going to write down iron oxide because I do that so often. And then we have then 55.85. Let's do some canceling. Answer. At 0.1515 grams of the iron ions. Divide that by the initial. (54.2%) is our final answer for that one. All right, guys, that was, I think, the last problem here on this. Good luck. Let me know if you have questions.